freedom of saying things like it's facing downward, it got wider, it got narrower. We're now going to clean up that language a little bit and state it a little more clearly in the correct mathematical terminology, okay? So we are going to look at some different types of transformations. We're going to summarize them, and we're going to try to use them and understand them on the front of this page. So turn the page over on the back for a minute so we can just write down some summary information. So what are the different types of transformations? Okay, so translations are one type. Cool. Reflections. Kylie? Rotations. What else? Okay, dilation. Yeah, so we're actually going to use a different word for dilation. We're going to use compressing or stretching, so we're going to look at it in both directions. Sam? Yeah, they said it at the beginning. So we're actually going to focus on 3 different types instead of 4. We're going to do reflections, translations, and stretches and compressions kind of fall into the same category as for us. We're not going to do rotations because we can achieve the shape we want with these other things without doing that, okay? So let's write those 3 topics on there. Oh, thanks. Okay, so let's go ahead and write them. We're going to have reflections is one category. Oh, and my pen is not working very well, so I apologize. I'll fix it. Okay, so reflections. We're going to look at translations. And we're going to look at stretching and compressing. So when you guys think about this, we've actually done all of these before, okay? And on the front side of this paper, it has some greatest integer function examples because that's a really good function to look at with these because it helps you see each type of transformation really separately because of the way the steps work. What did we see in our equation that caused a reflection when we were doing the greatest integer function and studying it? Kylie? Good. So negative sign and whether it was outside or inside the brackets created a different type of reflection. So we're going to speak a little more generally right now. I'm not going to write the equation with the brackets. We're just going to say f of x is our function. Today we're going to use greatest integer function, but the things that we're developing are true for all functions. So they're true for square roots, quadratics, cubics, greatest integer function, absolute value function. If you multiply a negative outside of the function, this would be considered outside of the function because it's in front of the entire thing right here. So it's like you already calculated the y value, and now you're taking the opposite of that. Okay? So this negative affects the y values. The numbers after you have already rounded them if you're using greatest integer, or square rooted them if you're using square root or anything like that. So when you guys change y values, think about a graph. If a point was above the x-axis, meaning it had a positive y value, and then you go and change the y value to the opposite of what that is, what kind of movement does it cause for the point? Nick? Okay, so not diagonally though, because if we're only changing the y's, so the x and the y's would be diagonal, but if we're just changing the y's, this point would end up just down here, right? The x would stay in the same place, and it would just change the y. And the opposite is true. So if I was a point down here with a negative y coordinate, and I'm just changing the y, that point would flip up and have a positive y coordinate. So this negative out here is affecting the y values, what you have after your function is done. And by changing the y values, you're causing your graph to flip or reflect over the x-axis. Whenever this type of transformation, we're going to label it as a reflection over the x-axis. Okay? And does everybody understand? I'm saying it's over the x-axis, but the negative is actually affecting the y values. Okay? That's what would make something jump to the other side of the x-axis, is to change the y value to the opposite. So the other option for the reflection is if that negative were inside multiplying x before you ever did the function. So before you rounded, or before you took the square root or the cube or whatever you were doing. So it's in here multiplying x by a negative before you do whatever function it is that you're doing. Okay? So in this case, the negative is affecting the x value. So points with positive x values would be over here on the right side of the y-axis. But if you then take the negative and take the opposite of this positive x value, where is this point going to end up? Riley? Good. Across the y-axis over here on the other side. Things that had positive x values will then be flipped on the other side and have negative x values. If you had a negative x, it would flip it over here and it would have a positive one. So this negative is affecting the x values, but when you change the sign of the x values, you're flipping or reflecting over the y-axis. So this transformation is also causing a reflection, but we need to understand that this reflection is happening over the y-axis. Okay. Is everybody okay with anytime you see multiplying by a negative, you should think reflection? And then depending on whether the negative is affecting the inputs, the x's, or the outputs, the y values, will change which type of reflection it is. Okay? When you label it, you can't just say reflection. You do have to say over which axis so we know what's happening. Okay? All right, translation. So what does a translation do to your graph? Someone new that hasn't talked to us. What kind of this? Yeah. Okay. Good. Left and right or up and down. What do we see in the equation in order to cause a translation? What did we see with our steps in order to shift left and right or up and down? Sam? Good. Our h and k values, which were being added and subtracted to things. So if we were multiplying by negative, we see reflections. If we're adding or subtracting stuff, we're in the world of translations. And again, there's kind of two places that you could add or subtract amounts. You could be adding or subtracting them to the x value, or you could be adding or subtracting them to the y value. So if they were being added or subtracted to the y value, meaning you finish the function calculation, you do the square root or the greatest integer function or whatever, and then after that, you add on a value, that's where we saw that k value. This causes a vertical translation. And then after that, you need to state whether it's up or down and how many units. So if I add 5, I would say it's a vertical translation up 5. Okay? Yeah, Sam.
It's both h and k. Can you say it's like translating along the vector?
Yeah. Yeah, that's fine. Mm-hmm. Okay. So the next way that we could see the translation is if something was being added or subtracted with x. But remember, we did the exploration and it didn't really look how you expected it to look. When inside the function you put an x plus 1, you didn't see the function shift 1 to the right. You actually saw it shift 1 to the left. So that's why they established this notation of using a minus sign here so that when you figure out the correct h value, it is actually working with your left or right, depending on if it's negative or positive. So this is going to be your horizontal translation. And with this, you need to talk about going left or right. So what caused stretches or compressions? Thomas? Good. Okay, and not just multiplying by a negative by using a number, right? Yes. Same thing. Okay, so slope in a line is what caused those changes. It caused stretching or compressing, but we can only use the word slope when we specifically talk about lines. So we have to kind of split it now into two pieces. Something is changing our graph vertically and something else might change it horizontally. Because you saw with the steps, different numbers in different places controlled the two different distances, not just one number. So stretches and compressions are caused by numbers multiplying stuff. So if you're multiplying outside of the function, that means the number would be in front of the radical or in front of the absolute value bars or in front of the greatest integer function bars. The rounding is separate from what's happening with the multiplier, okay? So when we were using the greatest integer function, I'm going to use that one as an example so that we can remember. What would happen if you took your function and changed it to something like this? What happens, this would be an example of this a value out in front of the greatest integer function multiplying the function. So it would be an example of this type of setup. Okay? What would the number 3 do to our steps in this graph? Cole? Good. It would increase the vertical distance in between the steps. Okay? So we would actually call that now a vertical stretch. It's like someone grabbed the graph on the top and the bottom and literally just pulled it and stretched the graph further and further apart vertically, causing bigger gaps between the steps, causing them to get further away from the x-axis. So when this number was a number bigger than 1, we were seeing a greater distance or a stretch vertically. So when the absolute value of a is bigger than 1, we see a vertical stretch. Okay, why did I use absolute value bars on a? That means I don't care if a is negative here. I'm not talking about that part of it. I'm just talking about the number part. If a was negative, what would that mean? Cool. No? Olivia? It would be a vertical stretch still. Here. Good. It changes the way that it's facing or looking. It means a reflection, right? So A has 2 parts to it. The negative part needs to be treated like a reflection. The number part is telling us stretch or compression. So here in your notes, when you see me use the absolute value bars, I'm using that because I'm not caring about the negative. I already talked about what the negative would do over here. Okay? Now I'm just wondering what the numbers are going to do. All right? Okay, if the a is less than 1, then that causes a vertical compression. So compression is like squishing them closer together. So if instead of 3, they had put 1/3 there, our steps would only be 1/3 of a unit apart. It was like we took the parent function, where they're 1 unit apart, took it vertically, and just squished all the steps closer together vertically. That's why it's called a vertical compression. Okay? All right, so what happened when instead of multiplying out here, we multiplied a number inside of the brackets? Okay, so what happens when we do this? The multiplier is multiplying to x instead of after the function is done. Yeah, Thomas. Good. It's going to cause a horizontal stretch or compression. Okay, so we're still going to have these 2 categories where we can have a horizontal stretch or a horizontal compression. And then the question is, which b values do which? And these ones were a little bit tricky, right? When somebody gave us this equation, so I'm just writing this momentarily for us to look at. When we put a 2 in here multiplying x for our steps, what actually happened to our steps? Cool. They were cut in half, right? So the 2 did actually mean something. It meant that x was getting through the values twice as fast as it used to, but that meant now it only took half the distance to reach the next y value. So we trained ourselves that when we see this, it does mean something, but it's not the same thing we're measuring on the graph. The thing we're measuring on the graph actually uses the reciprocal of this when we looked at it, right? So this is a b value that's bigger than 1, but it made our steps be half a unit long. So when the b value is bigger than 1, it's like taking our graph horizontally and squishing our steps so that they're shorter or closer to the y-axis. So a b value bigger than 1 actually causes a compression because we don't use that number that's bigger than 1. We use the reciprocal of it. Okay? Which means when the b value is smaller than 1, like a half, because we use the reciprocal of it, we're actually getting that stretch type of component. Okay? So now when we look at things, we're going to have to be able to label them appropriately. If we're saying vertical stretch or compression or horizontal stretch or compression, those are the words you would say. If you're using translations, you should be able to talk about the direction and how many units they're going. Up 5, down 8, left 3, right. And reflections, you should be able to list over which axis you are reflecting. I want you guys to take like 30 seconds in your group and see if everybody understood each of the translations or transformations, excuse me. Okay, so we're going to first look at this one. So first there's a notation thing here. It's here on purpose. This is kind of a pre-calculus idea of can you use the notation correctly in writing the function. So this says you're writing a new function called g of x, and they're telling you that g of x is equal to 2 times f of x. Okay? What is f of x? Look back at the directions at the top of the page. Nick? Okay, but it's not absolute value, right? It's the weird little brackets. Yeah. So it's greatest integer function. So f is defined as the greatest integer function. Okay, but even without knowing that, we'll rewrite that in just a minute. With a 2 out here, I should be able to tell you what's happening to this function as far as transformations go, even if I have no idea what the function is. Like, if I don't know what f is, I can still tell you that g is f after f has had this done to it. What's being done to f to produce g? A vertical stretch. Because 2 is multiplying out here, it's like the A position, right? So it's definitely going to multiply it by 2 and cause a vertical stretch. So we're going to have a vertical stretch. Since they did define this function for us, we can rewrite this without using f. It would basically be 2 times. And since we're using this very specific greatest integer function this time, that's what g would look like. And now we're going to graph the g function on the graph. Okay? Did we shift at all our starting point of our greatest integer function? No. So it's still at 0, 0. Should I still go to the right and up to form my steps? Yes, because there were no reflections. So I'm going to start at 0, 0. I'm going to go to the right and up. The 2 is only going to affect a vertical stretch, which is only changing the vertical distance. So I will plot my point, go to the right, finish my step. Sorry, a little hard for me. These squares are kind of small. I'm going to go up 2 units instead of 1, though, to draw my next step. Okay? And then I can continue that pattern. So this graphing part is technically something that you guys have already done, right? This was on your last test to graph the greatest integer function. Oh, sorry, my pen is not very aligned. The new part here is understanding some notation and that these transformations aren't just like making them more apart, but they have a very specific name as to what they're doing to the graph. Okay? All right, now I want to compare that one to the third one here that looks really similar but is slightly different. What's the difference between the one we just did and this one right here?
The 2 is within the parentheses.
Good. The 2 is within the parentheses. First, before we write the new equation, who can tell me if the g function is the f function with this 2 multiplying x? In general, what transformation is happening to turn the f function into the g function? Riley? Okay, either a horizontal stretch or compression. And so to decide which one, here it says 2, but what does that mean we're going to actually use on the graph? Half. And when we use a half, that's going to actually compress things, okay? So what I'm seeing happening here is a horizontal this time, because it's in there happening to x, compression. Okay? And my equation would be greatest integer function, and the 2 is in there with x. Okay? And so for this specific function, the greatest integer function, what does that horizontal compression mean for me when I go to draw my graph? Ruby? Good. My steps are only half a unit long, which clearly I'm not going to be very successful at with these graphs, so I'm going to be smarter than the graph and rescale it. I'm going to call each, like every time there's 2 lines, I'm going to call that 1 on my graph, okay? Same vertically. So that when I go to plot this, okay, I'm going to start at 0, 0, and my steps are going to be half a unit long. So I'm starting at 0, 0. I go half a unit long, okay? And then I go up a unit and make my next step. Okay. So it looks like I went up 2 units, but I didn't because do you guys see how I numbered my graph? Okay. Every two blocks is 1. I don't care how you do it. You guys can write a little bit better on your grid than I can up here. Okay? Is everybody okay with this idea? Formations have really specific names now, and we learned a little bit about how we can use other notation to write them. You technically now, if you understand all of this, have the skills to go do the homework that goes with skill 1. Again, is it due? No, I'm not going to check any of them this week because I'm not going to be here at the end of the week. We're going to kind of shuffle through the curriculum. But on Monday, everything that should have been done this week will be done. So if you have a lot going on later in the week, you should start maybe skill 1 homework tonight. If you don't, then you won't. So what you're going to do right now is you're going to work on finishing the front page of this. I'm going to walk around and help you guys. You're going to work with the people in your group, okay? And then tomorrow we'll look at the answers to this and make sure everybody fully understood it.